Okay, so we're pretty much done with showing you different kinds of functions. That's been the bulk of precalculus, showing you rational functions, polynomials, exponential functions, trigonometric functions. That's been the bulk of your time. Now we're not going to show you any new functions, but we're going to talk about properties of that functions. And the properties we're going to talk about are limits. This is a really intuitive concept, and it applies to all the functions we've been talking about, except the very early ones, where we had functions which just took one point and assigned it to another one. You know, something like this: x, f of x. These are discrete points. The other functions we have can usually be graphed, and that would be continuous. We won't worry about too much what that means. That's a whole area in itself. But we'll be talking about the limits of functions. And limits, you've sort of already talked about this when functions go to infinity. Sometimes we say the limit as x goes to infinity is infinity, for example, for some polynomials. Alright, but let's talk about other limits. You've seen functions that look like, say, one like this, and it has a hole here. Say it has a hole at, say that's 4, and this is f of x, this function, whatever it is. So, f of 4 does not exist. But you can see as you get closer and closer to 4, you'd still get numbers that are closer and closer to 4. So you go in from, like, say what this was, a 3 here. So you went 2.999, you get 3.999. You get closer and closer as the number gets closer and closer to 4. And this is what we're talking about for the limit. So here, although we can't say what f of 4 is, we can say the limit as, so here's the x value. As x gets closer and closer to 4, this value gets closer and closer to 3. So as x goes to 4, the limit of f of x as x goes to 4 equals 3. Right? It doesn't, the limit of, should have been 3. F of 3 equals, does not exist. F of 3 looks like it should be 4, but there's a hole there. Sorry. F of 4 should be 3. The limit of f of x as x goes to 4 is 3. So this way we can talk about what happens even though we have a hole here. There's some other terminology. Sometimes we may have a function which does this. Comes up and has a hole, well, makes not a hole there, and goes on to be another function, this function here. And the question is, what is the limit for this point here? Let's say this was a different scale. Let's say this was 5 and this was 4. What is the limit of this function? This is a broken function. It's not continuous. We haven't really talked about these kind. We'll call this g of x. What is g of 5 here? You can see it's a dot here. Say this was 5 up here. G of 5 does indeed equal 4 if this graph is accurate. And we're just going by this graph. Alright? So what is but you can see the limit. If you come this way, you don't end up at 4. As you get closer and closer to 5 from this side, you don't end up at 4. You end up at 5. So we have special terms for limits. Coming this way, we say this is the limit as x goes to 5 from the minus direction. There's an arrow. And as x goes to 5 from the minus direction, this ends up being 4. So the limit of g of x as x goes to 5 from the minus direction is 4. And this is called a left-hand limit. kind of a bad term because, well, I guess it's okay. I'll tell you why it's bad in a second. Well, if we come the other direction, this is called the plus direction. If we're coming down this way, the limit as x goes to 5 from the plus direction is 5. The limit of g of x as x is 5. Sort of these functions are defined by these graphs. We could easily put functions in here, and we will put analytic functions in a second, but we're just looking at these. So these two things are not equal. This is, of course, the right-hand side. I'm just going to abbreviate it. Right-hand side limit. Now, for a limit to exist at a point, the left-hand side and the right-hand side limit have to be the same. So here we say the limit as x goes to 5 without a plus or minus of g of x does not exist. So there just isn't a limit. It's different coming from both directions. Alright? So this is important terminology. It's pretty intuitive what's happening. You can talk about limits of regular points too. Say we had y equals x squared. And we want to talk about the limit as x goes to 2. Well, this is simply going to be a nice little parabola here. And as x goes to 2, this is going to go to 4. And indeed, the number, when you put in x equals 2, you get y equals 4. So the limit, we'll call this h of x instead of y, too. It's another function. So the limit of x is 2 of h of x does equal 4. Coming from this side, from the left-hand side, it goes to 4. Coming from the right-hand side, it goes to 4. And it actually is 4 at that time. So this is, I mean, it's not very helpful. We're not going to be doing this too much. But just so the limit works everywhere. And so we can easily talk about the limit of a regular point on a graph. It's when things happen like this that we get something weird. I'm going to show you one more example like this, and then look at some analytical ones. Let's say we had some weird function like this, but here's the axes. Say this is 6 out here and this is 4. But at this point there's a completely different value. So there's g of x. I'm going to call this a piecewise function. I should have made it a nice function. Let's make it a nice function. Let's go with our standard parabola. Here we have 2, and this will be 4. But we have a hole here at 2. So we say that this will be g of x. G of x equals, and we put these big braces, say x squared if x is not equal to 2, and we'll say it equals 6 when x equals 2. This is sort of a weird thing to do. This is called a piecewise function. P-I before E. Piecewise function. It's defined in different parts. And these can get more complicated. You can have 3 or 4 or 5 different parts of these functions, depending on what x values they have. So take a look at this thing. As we approach to from this direction, we get closer and closer and closer to 4. As we approach from this direction, we get closer and closer to 4. So the left-hand limit is 4. The right-hand limit is 4. But the actual value at the point is something completely different. But the left and right hand limits are the same, so we do say that the limit as x goes to 2 of g of x equals 4, even though the actual value at 4 is 6. Alright, so it's a weird discontinuity. I'm going to do another one. Well, I'll just talk a bit about this. You will remember equations such as this, x squared minus 1 over, say, x minus 1. Remember things like this? So here you can factor the top. It becomes x plus 1, x minus 1, and then you have x minus 1 down here. So you can sort of simplify it, but you have to make you have to explicitly say that x can't be equal to 1. Because the original function, these two are not the same function. We have simplified this, and in doing so we lost a special condition that you can't have 0 in the denominator, so x can't be 1. You can write it as, it'll graph out like this. Let's quickly graph that. See, when x equals 0, this equals 1. So it's a line, slope 1. But when it comes out here to point 1, there's a hole there because x can't equal 1. But we can still talk about the limit as this function goes to 1. So the limit, the right hand, let's start with the left hand side limit, as x goes to 1 from the minus side, 1, and this will be x plus 1, and that will be 2. So the limit of f of x as x goes to 1 from the minus sign is 2. The limit as x goes to 1 plus f of x is also equal to 2. Even though we can't have this value at 1, these two match, and this is a nicely behaved function, so we say the limit as x goes to 1 of f of x equals 2. So these things will come in handy very late on. They're bread and butter of calculus. Alright, so that's a little bit of new terminology. No really new concepts other than this approaching from the left and approaching from the right. And we will go on to look at some more functions which may have limits. They have limits existing here, and they may not. And this way you'll have a nice introduction to limits. Okay.